In this video, we're going to look at an example where we apply the eigenvalue method for solving systems of differential equations in the case when our coefficient matrix has complex eigenvalues. So recall that in order to solve a system of differential equations that has been written in matrix form as x bar prime equals ax bar, we first find the eigenvalues and corresponding eigenvectors of the coefficient matrix A, and then form solutions using the fact that the general solution x will be an eigenvector v times e to the lambda t, where lambda is the eigenvalue corresponding to the eigenvector v. Now, there are three cases that need to be discussed. The case when the matrix A has real distinct eigenvalues. We did that in a previous video. The case where the matrix A has complex eigenvalues. That's the focus of this video. And then finally, the case when the matrix has repeated eigenvalues. We're not going to do that in this course because of time constraints, but I'm happy to discuss that with you if you are curious. All right, so here we go. Let's start with just a big picture overview. So if we have a system of differential equations such as x1 prime equals 3x1 minus 13x2, x2 prime equals 5x1 plus x2. So big picture, when we go to solve this system, our solution is going to require that we be able to state explicitly what x1 of t and what x2 of t are. We need two solutions. We need to know what x1 is and we need to know what x2 is. Now, the key idea in the case when we have complex eigenvalues is that we're going to use one of our complex eigenvalues to write a solution, eigenvector v times e to the lambda t. And then in order to get our two different solutions, we're going to let x1 essentially be the real part of x and x2 be the imaginary part of x. And so therefore we'll see that we're only going to need one of these complex eigenvalues. They always come in pairs, right? The complex conjugates. They always come in pairs, but we'll be able to get away with just using a single one of them to solve the entire problem. Okay, so that's kind of a big picture overview. Let's get into the example. So suppose we want to solve the system. x1 prime equals 3x1 minus 13x2. x2 prime equals 5x1 plus x2. Including the initial data, x1 of 0 is 3, x2 of 0 is negative 10. Okay, so first we convert the system into matrix form. X bar prime equals our coefficient matrix, 3, negative 13, 5, 1 times x. And our initial data, x bar of 0 is 3, negative 10. We need to find the eigenvalues for our coefficient matrix. So we want to find all numbers lambda such that the determinant of lambda I minus a equals 0. Now in this case, lambda I minus a is the matrix lambda minus 3, positive 13, negative 5, lambda minus 1. We compute the determinant of this matrix, lambda minus 3 times lambda minus 1 plus 65. Multiply out lambda squared minus 4 lambda plus 68. And then if we were to say complete the square, there's of course a lot of different ways to find your roots in this case, but if you were to complete the square, you could rewrite this equation as lambda minus 2 squared plus 64. And therefore we have complex eigenvalues of 2 plus or minus 8i. Now, as I said in our big picture scenario, we're only going to need one of these complex eigenvalues. So I'm going to do the rest of the problem using 2 plus 8i. You could also use 2 minus 8i and get the same answer. Here we go. All right, so I'm going to focus on the eigenvalue 2 plus 8i. We need to find the corresponding eigenvector. So we need to solve the equation 2 plus 8i times the identity matrix minus our coefficient matrix of a, x equals 0. To help us do this, recall the form of lambda I minus a. So we're going to substitute in lambda equals 2 plus 8I, and that will give us the matrix. Negative 1 plus 8I, 13, negative 5, and 1 plus 8I. Now, you can use either the first row or the second row moving forward. If we use the second row, this tells us that negative 5x1 plus 1 plus 8I x2 must equal 0. And if we solve that equation for x1, we see that x1 is 1 plus 8I x2 divided by 5. So if we let x2 equal t, our eigenvectors are all scalar multiples of the vector 1/5, 1 plus 8I, 1. Or if we want to get rid of the fraction, we can say that our eigenvectors are scalar multiples of the vector 1 plus 8I, 5. Okay, now since we've got an eigenvalue of 2 plus 8I with corresponding eigenvector 1 plus 8I, 5, then the solution corresponding to this eigenvalue and eigenvector would be e to the 2 plus 8it times the eigenvector 1 plus 8I, 5. Now, the problem with this solution is that it has complex numbers in it. So we want to eliminate the complex numbers in both the exponential and in the vector itself. To do that, we're going to use Euler's formula. So you may remember from class Euler's formula, e to the a plus ibt, we can rewrite as e to the at times cosine of bt plus I sine of bt. So we're going to apply that formula to e to the 2 plus 8it. It will expand out to e to the 2t times the cosine of 8t plus I sine of 8t, and then times our vector 1 plus 8I, 5. All right, so we're going to multiply the cosine plus I sine times our vector. So we get cosine of 8t plus 8I cosine of 8t plus I sine of 8t minus 8 sine of 8t. And then for the bottom row, 5 cosine of 8t, 5I sine of 8t. All right, we're going to pull this matrix apart into the real parts and the imaginary parts. So for the real part, we'll have an e to the 2t times cosine of 8t minus 8 sine of 8t. And then in the bottom, 5 cosine of 8t. Plus everything that has an I in it. So an I e to the 2t times 8 cosine of 8t plus the sine of 8t, and then 5 sine of 8t. So we pulled it apart into the real part plus our imaginary part. And so we can think of this real part as u of t and this imaginary part as v of t. Now it turns out that we can show that the u and the v here are two linearly independent solutions to our system of differential equations. So we're going to use these two solutions to form our general solution. Okay, so our general solution will look like x of t equals a scalar multiple of that real part. So c1 times e to the 2t times the vector cosine of 8t minus 8 sine of 8t, 5 cosine of 8t, plus c2 times the v, which is e to the 2t, 8 cosine of 8t plus sine of 8t, 5 sine of 8t. Great. So now we can apply our initial conditions. We know that x of 0 is 3 negative 10. So we're going to apply those initial conditions to our general solution. And that tells us that 3 negative 10 is our x of 0. And if we let t equal 0 inside of our general solution, then our general solution simplifies to C1 times the vector 1, 5 plus C2 times the vector 8, 0. So focusing on the first component, we get 3 equals C1 plus 8C2. Focusing on the second component, negative 10 equals 5C1. Solve that system. C1 is negative 2, C2 is 5/8. So in our general solution, we're going to replace C1 with negative 2 and C2 with 5/8. So there we go. And so our final answer, if we expand along the top row, that tells us that x1 is e to the 2t times 3 cosine of 8t plus 133 over 8 sine of 8t. And if we expand along the bottom row, x2 of t is e to the 2t times negative 10 cosine of 8t plus 25/8 sine of 8t. So that's our final answer to the problem. Now, observe one more time. Since we were able to find two linearly independent solutions, an x1 and an x2, with a single eigenvalue, we do not need to use that second eigenvalue of 2 minus 8i at all. So when we're working with complex eigenvalues, pick one of them and you're able to get everything you need out of that single one. All right, that's all for now. Thanks, guys. Bye.